Continuing on to the next page. Here's an application now, and I really love this page because in one page you're going to encounter three of the really big ideas. Look, here's the gradient vector, here's the magnitude of the gradient vector, and then here's the directional derivative. You know, half the battle is just understanding all the symbolism that's being used here. So even though there's not a vector symbol, no arrows or I's and J, I don't know, whatever things, we just know that that symbolism here, now that we know, is a gradient vector. So let's start there. So gradient vector, the gradient of P, and let's start at any location xy, is the partial derivative with respect to x in the I direction, partial derivative with respect to y in the j direction. So that's the definition of the gradient vector, and in module 6 you learn more about where that all came from. So I like to kind of do my work on the side here, my derivative work. So let's work on the derivative, partial derivative with respect to x. So if we're taking the partial derivative with respect to x, that means we want to get the changes in p relative to changes in x while y is constant. So it might be useful to actually do this. That fluid pressure could be expressed as 1 plus, now if y over 100 in the context of a partial derivative with respect to x, if y over 100 is a constant, you could just think of it as like constant times x squared. So saying x squared y over 100 is the same as saying y over 100 times x squared. I hope you can see that they're algebraically equivalent. The reason I like to do that is taking the derivative now is pretty straightforward. It's just a power rule. So derivative of a constant is 0 plus the derivative of this with respect to x. The 2 comes out front. So it'll be 2y over 100, otherwise known as y over 50. And then decrease the power by 1. Now we could kind of go back to this symbolism here where we put everything in the numerator and call it x times y over 50. Maybe we like that. Now similarly, we can do some work with the partial derivative with respect to y by expressing this a little bit differently. Now if we're taking the derivative with respect to y, that is changes in p relative to changes in y while x is being held constant. And so maybe we would write it this way, x squared over 100 times y. It's just a linear expression. I forgot my 1 plus. It's just a linear expression. So the derivative would be, well, the derivative of the constant 1 is 0, and the derivative of a constant times y is just that constant. You know, like think about the derivative of 4y would be 4. The derivative of 57y would be 57. All right. Now, nothing we can really do to that. Now, in each case, we're particularly interested in the gradient vector at the location at the point 1, 2. And so let's evaluate both of these at the point 1, 2. So if x is 1, y is 2, 1 times 2 is 2, and we can simplify that. Partial, that was with respect to x. With respect to y at 1, 2, if x is 1 and y is 2, but if x is 1, 1 squared is 1, 1 over 100. All right, so the gradient vector of p at the point 1, 2 is the partial derivative with respect to x at the point 1, 2. Notice it's a vector. Make sure you're using some kind of a vector notation as you do this. And then the partial derivative with respect to y at the point 1, 2 was 1/100th j. And then the magnitude of that vector. Well, if we think about vectors as horizontal, vertical components, the magnitude is just that hypotenuse. So thank you, Pythagoras. The magnitude of the gradient vector at 1, 2 is just going to be the square root of 1/25th squared plus 1/100th squared. Now go ahead and compute that if you haven't already. I've got it over here as a decimal approximation, 0.041. Great, computations are awesome, but hey, let's be honest. You could have thrown all this into Wolfram Alpha and done it just as well. So that's not really the important part for a human being. The more important part is this, because Wolfram Alpha does not know how to do this. Interpret them in the context of this problem. So from Module 6 and even from previous on this page, we can think about what these things really mean. So the gradient vector, first of all, is a vector. So the gradient vector points you in the direction of the greatest increase. Let me go back to this picture. I know it's not the right context, but the picture still works. Remember how the gradient vector was perpendicular to the level curve at any point? That's the special feature, like geometric feature of the gradient vector. If it wasn't perpendicular, like let's say this is not true. Here, let me do it in red. This is not true. But suppose a gradient vector was like meandering its way like this. Do you see that the value of whatever what is this? This was temperature, that's right. The temperature increased, but it increased over a big distance. That's not going to be a big rate of change. As opposed to, now the temperature has the same increase, but over the smallest distance it can have. The smallest distance that we can have to change from one level to another would be along that perpendicular path. And so, a gradient vector, one of its features or uses or purposes or the value and why we would want to consider it is it gives you the direction of the greatest rate of change. So here's what we might say. If you're at the point 1, 2, the bottom, remember we're at the bottom of a body of water, so you're like a critter scampering along the bottom of the ocean, bottom of a body of water, and we put a coordinate grid over some region, and we go to the point 1, 2. At that point, the critter should move in the direction of this vector in order to see the greatest rate of change. So at the point 1, 2, 1, 2 would be like, say, here. I should move in the direction of 1/25th in the I direction, 1/100th in the J direction, not to scale. I should go that way in order to experience the greatest fluid pressure increase. Now, this is all metaphor, this is not like, this is what you want to do. If you're in the ocean, you want to move in a direction where you have the greatest change in the pressure. I'm not saying that. I'm just trying to metaphorically explain what that gradient vector does. So, metaphorically, if you're at the point 1, 2, and you want to experience the greatest increase in pressure, in fluid pressure in this case, then you should move in the direction of the vector 1/25th I plus 1/100th J. And if you do, this is the rate that you'll experience. So this would be a rate in, let's see, fluid pressure, X and Y are measured in meters, fluid pressure. So we'll just say, since they didn't give us specific units, so this would be an increase of 0.041 pressure units per 1 meter in the direction of that gradient vector. So if you move in the direction of that gradient vector, you will experience an increase in pressure of 0.041 units of atmospheres per meter, let's just say. And that will be the greatest rate of change. I promise you, if you tried moving in any other direction, the rate of change will not be as great as 0.041. It'll always be less. That's the value. Now, I think last week, I know last week, you had some explanation about why that's the case. I'll leave that to the last week's lesson. All right, so first of all, gradient vector. It's a vector. The direction gives the greatest rate of change. The magnitude of that vector tells you what that rate of change would be. Now, down here, we've got the directional derivative, still at the point 1, 2, But now they're going to send us in a different direction. So just to kind of give you the sense, the vector 3i minus j, now we're at the point 1, 2, let's say that's here. The vector 3i, so 3i minus 1j, not to scale, we would be heading in that direction. Now remember, we already know that at the point 1, 2, the greatest rate of change would be following that gradient vector. We are no longer following the gradient vector, which was kind of that away. We are now following some other vector, and we want to still find the rate of change. Now here's one thing I know for sure. Whatever we determine for this rate of change, I know it's going to be less than the 0.041 that we already saw. Let's find out if I'm right. So, directional derivative looks like this from previous. The directional derivative at the point 1, 2 is found by taking the partial derivative with respect to x at the point 1, 2, multiply it by the direction I component of the unit vector. See, u is a unit vector, remember, plus the partial derivative with respect to y at the point 1, 2 times the j component of that unit vector. Notice, dot product, scalar, this is going to give us a scalar, and I'm guaranteeing, I'm calling my shot right now that whatever we get here, it's going to be less than 0.041. All right, let's start working on it. Now, because we've already done the gradient vector work from before, let's use it. Remember the 1/25th and the 1/100th? So I know this is going to be 1/25th times something, and I know this is going to be 1/100th times something. Now, u is a unit vector in that direction. Now, so here's actually the 3i minus 1j. It's this vector. This vector is not a unit vector. It does not have a magnitude of 1. Here's how I know. The magnitude of that vector is 3 squared, 9, plus negative 1 squared, 1. That vector has a magnitude of the square root of 10, a little over 3 units long. I want to scale this thing back to have just a magnitude of 1, but still be in that direction. So the way we accomplish that is we take that vector 3i minus 1j, and we divide by the square root of 10. Because if you take the length of the square root of 10 and divide by the square root of 10, you've scaled it by a factor of 1 over the square root of 10, thus scaling it down to just 1 unit. So divide by the square root of 10, divide by the square root of 10. All right, so back over here, that u1 would be 3 over the square root of 10. That u2 would be negative 1 over the square root of 10. And let's just grab a calculator now and compute. Now notice again, all scalar. A directional derivative is a derivative. It's a rate of change. And so it's a scalar. It's not a vector. Only the gradient vector is a vector in this stuff that we're doing right now. And so we do the computations, and I've got it here. You can check my work. It comes out to be approximately 0.0348. Now these were pressure units, so often we use atmospheres. So at the point 1, 2, if you went in that direction, the pressure would increase by 0.0348 atmospheres per meter in the direction of that unit vector u. All right, so at the bottom of this page, there's some nice summary. So the vector, there's the gradient vector. The gradient vector points in the direction of, let's call it maximum increase. So again, metaphorically speaking, if you want to increase the output quantity, whatever the function's about, temperature, pressure, who knows what, if you want to increase that function at its greatest rate, move in the direction of the gradient vector. The scalar gives you the actual magnitude of that maximum increase. So again, metaphorically speaking, if you want to experience the greatest increase in your output quantity, what would that increase be? Well, do the magnitude of that vector and you'll find out. All right, I'll pause there for the next video. Hope that helps.